Hi, and welcome to the class on multivariable regression as part of our Coursera Data Science specialization. In this lecture, we're going to talk about instances where we have lots of potential predictors for an outcome rather than just a single predictor in linear regression. In any instance where you're using a predictor, x, to predict a response, y, and you find a nice relationship, if that predictor hasn't been randomized to the subjects or units, whatever you're looking at, then there's always a concern that there's another variable that you either know about or don't know about that might explain the relationship. And let me give you an example. Imagine if you had a friend that downloaded some data where they had all sorts of health information from people and also their dietary information. And this person said, hey, I found something interesting. Breath mint usage has a significant regression relationship with forced expiratory volume, a measure of lung function, pulmonary function. If you've ever gotten an asthma test, they'll measure your FEV. Well, you would be skeptical. I mean, there's very little basis for a biological relationship there. Breath mints are just sugar. It doesn't seem reasonable that they would impact lung function, but maybe. But what you'd really be thinking is, well, what other variables might be explaining this relationship? And you might come up with two hypotheses. One is this person dug through lots and lots and lots of variables and just found the one that was significant, and it's just a chance association. And that's the problem of multiplicity. Okay, so we'll talk about that in other aspects of this course and the inference course. But let's just assume that this person didn't do that. They looked only at a couple of variables and the multiplicity concerns weren't so bad. Then what would you think? Well, likely you would think, well, probably the real problem is smokers tend to use more breath mints, and smoking has this long relationship with lung function. So it's well established that chronic exposure to smoke or even secondhand smoke has negative impacts on lung function. So it's probably that. It probably has nothing to do with the breath mints. It's an indirect effect of breath mints through smoking, not a direct effect of breath mints on lung function. That would be your likely hypothesis. Well, how would you establish that there's a breath mint effect beyond smoking? Well, likely what you would ask your friend to do is, well, consider smokers by themselves and see whether their lung function differs by their breath mint usage, and consider non-smokers by themselves and see whether their lung function differs by breath mint usage, where you've sort of conditioned on smoking status so that you're comparing like with like. Well, multivariate regression is sort of an automated way to do that in a linear fashion. It makes assumptions, which is fair enough, but it does that sort of in an automated way. And we'll explain in this lecture in what way is it trying to sort of hold smoking status constant while looking at breath mint usage, and how it adjusts. And we'll also talk a little bit about its limitations. But that's the fundamental idea of what multivariable regression is trying to do. It's trying to look at the relationship of a predictor and a response while having at some level accounted for other variables. So in addition to the use of multivariable regression that I talked about in the previous slide, I wanted to also talk about another use of multivariable regression for prediction. It's actually a very good prediction model. So as an example, several of us around here engaged in the so-called Kaggle competition to predict the number of days that a person would be in the hospital in subsequent years given their claims history and number of days they were in the hospital in previous years. And this is of major importance to hospitals and insurance companies and healthcare providers for a variety of reasons. It's one of the main questions in that field. So in this competition, they gave you historic claims data, a lot of it actually, which had lots and lots of predictors, and the number of days that a person with several people of the insured people from this company were in the hospital for 3 consecutive years or so. And simple linear regression certainly wouldn't have been too much use here. It's good for looking at variables at a time really quickly, but if you wanted to get good prediction, you needed to do something more complicated. So there's multiple parts about this. So one of the main things is model search. How do we pick which predictors to include? That's an important component of this. And the other is to avoid overfittings. We'll learn that as you put enough variables into a multivariable regression model, you'll get zero residuals just by virtue of having included even random vectors into your regression model. So certainly there's consequences to throwing lots of garbagey predictors into a model, and certainly there must be consequences to omitting important predictors in a model. And in the practical machine learning class, which is also part of the specialization, you will learn a lot about model selection strategies as they relate to the idea of prediction. In this class, we're going to focus more on the problems from the previous slide, where we want to generate parsimonious models where we're deeply interested in interpreting the coefficients from the linear model. And so the prediction problems like this one are a little bit more geared toward our practical machine learning class, but I just wanted to mention that multivariable regression is a pretty good starting point in any prediction, any time where you're developing a prediction algorithm. What we found in that competition is that multivariable regression got you very close to the optimal or the winning entry, and lots of machine learning and random forest and boosting and all these other things, those only got you, minor bumps on top of that. And so, to get huge drops in prediction error, well thought out linear models sufficed, and then to get really minor increments beyond that, you had to throw a lot of computing. And to be fair, those did improve your chances, and we moved up a little bit in the leaderboard by adding some of these more complicated things, but it was remarkable how far you could get with just well done linear models. So our linear model looks an awful lot like our simple linear model. It's just that we have more variables. So our outcome, y, it might be insurance claims or forced expiratory volume, is equal to a bunch of coefficients. These are the beta terms. They're like the slope terms in simple linear regression, just now there's more predictor terms, more x values. So for example, one of these x1 might be breath mint usage, a binary variable, and x2 might be number of pack years, or how much the person smoked. And in the insurance case, x1 might be the number of insurance claims in the previous year, and x2 might be whether or not this person had a particular cardiac problem, something like that might lead toward information about hospitalization in the successive year. So here we just write out the linear model, and it just looks like the outcome is equal to a bunch of coefficients times predictors. Now, it's linear because it's linear in the coefficients. I'll reiterate that point in a minute. I would also add that the first variable is typically just a constant 1, so that there's an intercept that's included, a term that's just beta by itself, beta 0 usually, or beta 1. So our least squares, I think everyone could probably guess what the least squares is going to do. It's just going to look at the differences between the outcome and the prediction from the linear model, summation of the predictors times their coefficients. Because that's not necessarily positive, we're going to square it, and we're going to add it up so this difference for every observation equally weights into this loss function that we've created. So least squares simply wants to minimize this equation, and it's a direct extension of the equation we wanted to minimize when we had simple linear regression. And I would notice that the important linearity is linearity in the coefficients. So for example, if I take one of my x's and just square it, meaning every, if I have a vector in R that I've just squared every element of that vector and put that in as part of my model, then that will still be linear in the coefficient. The coefficient won't be squared. It will just be the x term. And so it's the important version of linearity is linearity in the coefficient. That's what defines a linear model. So let's talk about how you actually get the estimates, or how R or whatever figures these things out. And I'm going to go through a derivation, and again, if this is not your thing, then feel free to skip over this part of the lecture. Remember, if you have regression to the origin, you want a line that's forced to the origin that has no intercepts. You have a single predictor x and a single predictor y, and you want no intercept. The slope estimate was just this sum of the product x times y divided by the sum of the x's squared. We talked about that earlier on in the class. Now let's just consider, let's see if we can use that result to derive the least squares estimate when we have 2 regressors, and then I think if you've got the gist of this, you could see how it would work for 3 and how it would work for 4 and so on. Okay, so derive is maybe a bit of an ambitious term as to what I intend to do here. What I guess I mean is develop, and I'm going to ask for those that are interested to fill in the details on their own, but what I'm going to do is simply develop the estimator a little bit. And the reason I'm going to go through this development is I think it illustrates what multivariable regression is doing. If you're not too interested in this sort of development, then I think you could reasonably skip over this slide or this set of notes and not worry about it. But if you're interested and you kind of want to understand how multivariable regression works, I'm going to give a development that's more intuitive than what you would get with something like linear algebra. In addition, I have some videos on YouTube where I go through the linear algebra development if you'd like to watch those. But I don't think that that's actually necessary to sort of understand what's going on. So let's consider 2 regressors. We have summation of the outcome, yi, minus the first regressor, xi1 times beta1, minus the second regressor, xi2, x2i times beta2 squared. That's the least squares criteria that we would like to minimize. So for example, x1i might just be an intercept, and x2i might be some, is a covariate of interest, blood pressure or something like that. Okay, so here's the trick. Imagine if I were to just know beta 1 or fix beta 1. Then I get yi tilde, let's say, is equal to yi minus x1i times beta 1. And then this equation becomes summation yi tilde minus x2i beta 2 squared. Well, then this is exactly regression through the origin with just the single regressor x2i, but the outcome y tilde I. So we know what the estimate for beta 2 would have to be. It would have to be summation yi tilde x2i over summation x2i squared. Now, what you can do, this, and remember yi tilde, see, remember its definition over here. If we were to plug it in, that's a function of beta 1. So what I could do is, now that I know that my beta 2 has to satisfy this equation, I can take this and plug it back in here, right? Or equivalently back in here. And then what that yields is an equation for that only involves beta 1 and a regression through the origin for beta 1. And if you want to, you can fill in the rest of the details. What it works out to be, and this is the interesting part, is that the regression slope for beta 1 is exactly what you would obtain if you took the residual of x2 out of x1 and x2 out of y, and then just did regression through the origin. So kind of what multivariable regression is doing is it's the coefficient for x1, say beta 1, is the coefficient having removed x2, the other covariate, from both the response and that first predictor, x1. Similarly, the regression coefficient for x2, beta 2, is going to be what you get if you were to remove x1 out of both the response y and out of the second predictor, x2. We're going to go over this point a lot, and I know it's probably confusing to begin with, but it explains what multivariable regression is doing. A coefficient from a multivariable regression is the coefficient where all the other variables have been, their linear effect on that predictor and the response has been removed. And this is a very useful fact, and we'll exploit it in a variety of ways. So in case you skipped over that previous slide, I wanted to go through the result because it's important for your understanding of multivariable regression. So remember, we have 2 covariates in this case, an x1 and an x2, and of course one outcome, y. And we're interested in a model that has only the 2 covariates and a regression slope beta 1 for the first one and a regression slope beta 2 for the second. The result is that the fitted coefficient for beta 1 is what you would get with regression through the origin if I had removed the second coefficient, x2, if I had removed its linear effect from both the response y and the first regression variable, x1. So that's the sense in which multivariable regression, the sense in which the coefficient for x1 has been adjusted for the effect of x2, because the linear effect of x2 has been removed from both the response y and the first predictor, x1. Similarly, the same thing could be said about the coefficient for x2, beta 2. Once we get its estimate, beta 2 hat, it is what you would get if you were to remove the effect, the linear effect of x1 out of both the response y and the second predictor, x2. And this is why multivariable regression relationships are sort of thought of as having been adjusted for all the other variables. We'll go on in the next slide and talk about how this relates to a full multivariable regression where you have lots of predictors. So let's go through the case that we already know of simple linear regression, where one of our covariates is an intercept term and the other one is some covariate of interest. So here we have yi equals beta 1 x1i plus beta 2 x2i, where in this case I'm just going to assume the second one is the intercept term, whereas we usually assume that the first one is the intercept term, but that of course doesn't matter. So if we adhere to my rule that the estimated beta 1 coefficient is going to be the one that's obtained by getting rid of x2 out of the both y term and the x1 term, let's think about what we would get if we fitted x2 on y. Well, x2 is just an intercept, so as we know in intercept-only regression, the fitted value is just y bar. And so the residuals are just the observations yi minus y bar. In other words, the centered version of the y's. And then if we were to fit x2 on x1, again, x2 is just a constant. If we were to do the fitted values, the coefficient would just be x1 bar, the mean of that covariate. And so the residuals would just be x1i minus x bar, the centered version of that covariate. So getting rid of this intercept term from the y is just centering that variable, and getting rid of this intercept term from x1 is just centering that covariate. And then my fitted regression estimate is given down here, is just the product of the centered y's times the centered x's added up, divided by the sum of the centered x's squared. I give you that formula here and you can work with it, and it just works out to be the standard regression slope, the correlation between the x's and the y's times the ratio of the standard deviations. So now let's extend this to more than two variables so that we can start dipping into the idea of multivariable regression. So hopefully you see where we're going with multivariable regression. Our least squares criteria is now the distance between our observed outcome, yi, and x1 times its coefficient, all the way up to xp times its coefficient, the squared distances between those. If we only have two regressors, an intercept and a slope, this amounts to minimizing the sum of the squared vertical distances between the outcome y's and the predictors and the prediction on the line. If it's three regressors, an intercept and two regression variables, then the fitted line is, or the fitted construct is no longer a line, it's a plane, and the least squares criteria is minimizing the sum of the squared vertical distances between the outcomes and the plane. If we take more than three variables, an intercept, and then let's say three covariates, then we can't visualize it anymore. So, but it's sort of the generalized idea of the distance, the vertical distance between the y's, and some generalized version of a plane. And what we've seen is the idea that multivariable regression adjusts for the other variables in a sense by taking residuals. So for example, if we take this coefficient in front of x1, beta 1, the way in which we interpret beta 1 is that the remaining regression variables, x2 up to xp, have been linearly removed from both y and x1, and then the relationship between those residuals investigated by themselves. So in a sense, y has been adjusted for the remaining variables, x1 has been adjusted for the remaining variables, and we look at those two together so that beta 1 can be thought of as an adjusted effect, having adjusted for the linear relationship with the other variables. So what we're going to do now is go through some computer experiments to illustrate that this is how LM works. And then in the next lecture, we're going to go through some examples and how we interpret the coefficients in a context. So let's demonstrate how this works. So I'm going to do a simulation where I have 100 observations, and I'm going to generate 3 predictors, an x, x2, and x3, and they're all just standard normals. And then my y is going to be an intercept, which I'm just setting to 1, plus x, plus x2, plus x3. So all my coefficients are theoretically 1. So the population model used for simulation, they're all 1. And then I'm going to add some random noise. That's the error term. So let me get my residual for y, having regressed out x2 and x3. And remember, LM by default contains an intercept. So resid takes the residual. And then let's do the same thing for x. And remember, LM takes an intercept. So this is the regression of x with x2 and x3 and an intercept removed. And then I'm going to get the regression through the origin estimate with these 2 residuals. And that's 0.11053. And I can also show this with LM because I can do LM. The y is the residual y is the residual x, but I have to take out the intercept. And let me get the coefficient. Should just be the one number now, and show you that is it exactly the same thing. But now what I wanted to point out is that this coefficient is the same coefficient as if I regress y on x, x2, and x3, and an intercept. There you go. And you see the x term right here is exactly the same as the regression through the origin estimate with the residuals. So again, that just goes to show you the way we interpret, or the way in which linear models adjust the regression estimate with respect to the other variables. It's sort of like the effect of the other variables has been removed from both the predictor and the response. So let's go through how you interpret regression coefficients with respect to the model right now. And then again in the next lecture, we're going to go over specific contextual examples. So our regression predictor, given that our collection of covariates take a specific value, x1 to xp, is just the sum of the x's times their coefficients, right? That's our linear model. Well, just think if one of those regression coefficients, let's just take in specific the first one, is incremented by 1, right? So instead of taking the value x1, it takes the value x1 plus 1. Well, then that's just the same equation, but that first one is now x1 plus 1 rather than x1. So if I were to subtract these 2 terms, the expected value of the response, where the first coefficient takes the value x1 plus 1, minus the expected value of the response, where the collection of coefficients are just the x1 to xp values, then you'll see that that works out to be beta 1. So notice all these other x2 to xp were held fixed in all my discussion. So x2 to xp were held fixed, and x1 was incremented by 1 unit, whatever the units of x1 is. So the interpretation of a multivariable regression coefficient is it's the expected change in the response for a unit change in the regressor, but holding all the other ones constant. That's the essential part of interpreting a multivariable regression relationship, is it's holding the other ones constant. And that way, it also, the interpretation you can think of as being adjusting for the other variables, because we have to hold the other variables constant. So again, in the next lecture, we're going to go over a bunch of different contextual examples, but that's the mathematics behind the interpretation right there. And then I'm just going to go right now through a laundry list of the basic components of the linear model, because they're just exactly the same as in simple linear regression. So remember, if our linear model is our outcome y, is just now, instead of a simple linear regression, is the sum of a bunch of predictors times their coefficients plus an error term, and we're going to assume that error term is normally distributed, we get a bunch of properties. And so we're going to just rifle through these properties, and then I think when you go through the examples, you'll internalize them a little bit better. But these should all be pretty familiar, because they're basically the same as what we did for linear regression, just now we're plugging in some more coefficients. So our fitted response, for example, y hat at any specific value, is just plug in the fitted coefficients times those specific regressors, whether that's a new value or one of the observed values. The residuals is just the fitted value, y hat, being subtracted from the observed value. We're trying to minimize the sum of the squared residuals. The variance estimate is just the average squared residuals. We're just like, remember in our linear regression case, we divided by n minus 2, now we divide by n minus p. And that's kind of a technical point, because if you know n minus p of the residuals, you know the last p of them due to some linear constraints. So that's why we divide by n minus p. We don't really have n residuals, we have n minus p of them. But that's a minor point. You can think of the residual variance estimate is nothing other than the average squared residuals, for the most part, that n minus p part notwithstanding. So again, to get a predicted response at some new values, just we're plugging them into the linear model. If we have a new x1 to xp, we multiply them each by their respective coefficients and add them up, and that's our new predicted response. Our coefficients have standard errors. Sigma beta hat, let's say, for sigma beta 1 hat for beta 1, sigma beta 2 hat for beta 2. And we can test for whether or not specific coefficients are 0 with a t-test, because those, the beta hat minus its true value divided by this standard error follows a t-distribution. So all the things we knew about from linear regression carry over to multivariable regression. In addition, predicted responses have standard errors, and we can calculate prediction and prediction intervals just like we did in linear regression again. So again, I'm hoping that none of these facts are kind of news to you. It's almost identical to what we did in simple linear regression. We just have more terms now. And remember, in linear regression, we had two terms. We had an intercept and a covariate. Now we're just adding more covariates potentially. I want to end this lecture, before we move on to some specific examples, I want to end this lecture with just a general discussion of how important linear models are to the data scientist. Before you do any machine learning or any complex algorithm, linear models should be your first attempt. They offer parsimonious and well understood, easily described relationships between predictors and response. Now, to be fair, some modern machine learning algorithms can beat some of the things like the imposed linearity. Nonetheless, linear models should always be your starting point. And there's some amazing things you can do with linear models that you may not, just from this first treatment of them from this one lecture, think that would be possible. For example, you can take a time series, like a music sound or something like that, and decompose it into its harmonics. The so-called discrete Fourier transform can be thought of as the fit from a linear model. You can flexibly fit rather complicated functions and curves and things like that using linear models. You can fit factor variables as predictors. ANOVA is a special case of linear models. ANCOVA is a special case of linear models. You can uncover complex multivariate relationships with the response. And you can build fairly accurate prediction models.